Flame photometry. 2.1 Introduction. When sodium chloride is introduced into the flame, we may have observed yellow light. For the elements strontium, lithium red light is observed. That is, some of the elements when subjected to flame produce a light of particular color, that is of a particular wavelength which is characteristic of the element. The same fact is utilized in flame photometry. Flame photometry is based on the measurement of intensity of the light emitted when a metal is introduced into the flame. The wavelength of color produced indicates which element is present, and intensity of color tells us the quantity of the element present in the sample. Flame photometry is also called as flame emission spectroscopy because the atoms and molecules are raised to an excited state by thermal collision brought by using a flame. After returning to their lower or ground electronic state, the excited atoms and molecules emit radiations of characteristics of each element. 2.2 General Principles of Flame Photometry. The principle of flame photometry is similar to emission spectroscopy, only the source of excitation energy is flame. This is a lower energy source so that the emission spectrum is simple as it has few lines. The sample is introduced into the flame in the form of solution so that the technique is easy to quantify. As it is the emission spectroscopy, flame photometry is called as flame emission spectroscopy. General principle or the process of flame photometry is described in brief as, when a sample in the form of solution is subjected to a flame in the form of fine spray, the solvent is evaporated and the sample in the form of dehydrated salt is remained. Then the salt is dissociated into free gaseous atoms in the ground state. A certain fraction of these atoms absorbs energy from the flame and are raised to an excited electronic state. These excited atoms return to the ground state by emitting photons of characteristic wavelength. By measuring the wavelength of emitted radiations, we can determine the element present in the sample. While by measuring the intensity of emitted radiations, the concentration, that is the quantity of element in the sample, can be determined. The steps involved in flame photometry are summarized as below. 1. Vaporization. When a sample solution is subjected to flame, the solvent is evaporated and solid sample, or liquid, is converted into gaseous state, that is the sample is vaporized. 2. Atomization. The gaseous molecules are dissociated to form neutral atoms or radicals in the ground state, that is the gaseous molecules are converted into atoms. 3. Excitation. The excitation of atomic species due to absorption of energy from flame takes place. The atoms in vapor state are excited to higher electronic state, as they are unstable. After a very short time these atoms lose the energy and return to the lower or ground electronic state. During this transition the energy is emitted in the form of radiation. The wavelength of emitted radiation is characteristic of element present in the sample. If E2 is the energy of higher, excited, energy level and E1 is the energy of lower energy level, then the difference is energy emitted in the form of radiation, which is given as delta E is equal to E2 minus E1, which is equal to h nu, where h is the Planck's constant and nu is the frequency of emitted light. But we know that nu is equal to c by lambda. That is, E2 minus E1 is equal to h c by lambda, or lambda is equal to h into c, divide by E2 minus E1. The wavelength of the emitted radiations is the characteristic of the element present in the sample. Hence, by measuring the wavelength of emitted radiations the element present can be detected, and from the intensity of emitted radiations the quantity of element present in the sample can be determined. The flowchart of these events can be represented as given below. Liquid sample containing element aspirated into a flame, then formation of liquid droplets takes place, In next step evaporation of droplets, that is vaporization to gaseous state happens. Now the atomization process happens where dissociation of gaseous molecules into neutral atoms or radicals takes place, then formation of excited atoms, excitation, and emission of radiation from atoms. Now the wavelength and intensity of emitted radiation measured by flame photometer. Some of the neutral atoms or radicals formed in the flame may combine to form new gaseous compounds. The formation of these new compounds decreases the population of neutral atoms, hence the intensity of emitted radiations may decrease. This causes the chemical interference in flame photometry. The fraction of free atoms or the relative population of ground state, N0, and excited state, Ne, population at given flame temperature is given by Maxwell-Boltzmann expression as Ne by N0 is equal to Ge by G0 into e rest 2 minus delta E by K, T. Or Ne by N0 is equal to A into e rest 2 minus delta E by K, T. Where Ne equals the number of atoms in excited state. N0 equals the number of atoms in ground state. A is equal to Ge by G0. Equals is the ratio of statistical weights for excited and ground state. It is constant for given element. Delta E equals difference in energies of two energy levels. K equals Boltzmann constant. T equals absolute temperature. From above equation it is clear that the fraction of atoms excited depends upon the temperature of flame, so that, if the temperature of flame is higher, the number of excited atoms will be higher. Hence, fraction of atoms excited depends upon the flame temperature. So, controlling of flame temperature is important in flame photometry. The number of excited molecules decides the intensity of emitted radiations. Hence, intensity of emitted radiations may increase by increasing temperature. But this may not be true for all elements, particularly for the elements lithium, sodium, and potassium. As temperature increases, ionization of the atoms takes place instead of excitation. However, the temperature of flame is an important factor in flame photometry. To produce the flame, different types of fuels are used. Depending upon the fuel and oxidant, the temperature of the flame produced is summarized in below table. The temperature of the flame is controlled by several factors as follows. I. Type of fuel and oxidant. 2. Fuel to oxidant ratio. 3. Type of burner used in flame photometry. 4. Type of solvent used for the preparation of sample solution. As given by Boltzmann distribution, the energy available in the flame for exciting atoms is dependent on the flame temperature. Flames have only limited amounts of energy available compared to excitation sources, such as emission spectrographs or plasma emission torches. Due to which flames are useful only for the elements which require low amount of energy to become excited. For example, alkali and alkaline earth metals. 2.3 Instrumentation. Block diagram. A block diagram of the equipment used in flame photometry is as shown in below figure. The instrument possesses the same basic components as that of spectrophotometer, and these are source, monochromator, slit system, and detector system. The flame photometer also includes the burner, which is utilized for burning the sample solution and exciting the atoms produced in the flame after burning. The various components of instrument are described as follows. 1. Burners. The flame used in flame photometer must possess the following properties, functions. I. The flame should have ability to evaporate the liquid droplets from the sample solution and to form solid residue. 2. The flame should decompose the compounds in the solid residue formed, resulting in the formation of atoms. 3. The flame must have the capability to excite atoms formed and causes them to emit radiant energy. The temperature of the flame, which is primarily responsible for the occurrence of the above-mentioned processes, is controlled by the several factors which are summarized below. I. Type of fuel and oxidant and fuel-to-oxidant ratio. 2. Type of solvent for preparing the sample solution. 3. Amount of solvent which is entering into the flame. 4. Type of burner employed in flame photometer and v. The particular region in flame which is to be focused into the entrance slit of the spectral isolation unit. In flame photometry, several burners and fuel-oxidant combinations have been used to produce the analytical flame. Some of these burners are discussed below. I. Premix or laminar flow burner. A typical premix or laminar flow burner can be represented as shown in below figure. In this energy-type burner, an aspirated sample, fuel, and oxidant are thoroughly mixed before reaching the burner opening, and then this mixture enters the flame. Here, the gases move in non-turbulent fashion, that is in laminar flow. An important feature of this burner is that only a small portion, about 5%, of the sample in the form of small droplets reaches the flame and is easily decomposed, which means that an efficient atomization of the sample in the flame takes place. Larger droplets from the aspirator impinge on the side of the spray chamber and are drained off. Thus, in this burner 95% of the sample may be wasted, which results in a loss of sensitivity. However, this loss may be balanced against the loss of larger droplets. Advantages. I. The flame produced by premix bummer is noiseless, non-turbulent and stable. 2. In this burner, easy decomposition of the sample takes place, which results in an efficient atomization of the sample in the flame. 3. Premix burners can handle solutions up to several percent without clogging. Disadvantages. The main disadvantage of premix burner arises when the sample contains two solvents. When this is aspirated into the flame, the more volatile sample will evaporate in the spray chamber, leaving the sample in the form of undissociated atoms in the less volatile component. Thus, a smaller number of atoms would reach the flame. This will reduce the emission intensity, giving incorrect results. 2. Lundergraph burner. In a typical Lundergraph burner as shown in below figure, in this sample must be in liquid form. It is aspirated into the spray chamber. Large droplets condense on the side and drain away. Small droplets and vaporized sample are swept into the base of the flame in the form of a cloud. An important feature of this burner is that only about 5% of the sample reaches the flame. The rest of the droplets condense and are drained away. This shows a significant loss in atomization efficiency and hence, sensitivity. Difficulties may also arise if there is any selective evaporation of solvent in the spray chamber. Particularly, if there are two solvents, the more volatile solvent will preferentially evaporate, leaving the element of interest in the less volatile component, which may drain away, taking the sample with it. In this event, many of the sample atoms never reach the flame, due to which the emission intensity reduces and wrong results are obtained. Various devices like impact bead, ultrasonic vibrators, and more recently thermospray heaters, have been used to enhance the efficiency of burner at the nebulization stage in this type of burner. For example, an impact bead has the effect of breaking up large droplets as they emerge from the nebulizer, hence, increasing the number of small droplets and consequently the efficiency of nebulization. The atomization step is largely dependent on the efficiency of the nebulization, since the droplets must be evaporated and the residue must be broken down to liberate free atoms after introduction into the flame. Advantage. An advantage of the Lundergraph burner is that it is physically quiet to operate, which is a distinct advantage over the noisy total consumption burner. 2 mirrors. The radiation from the flame is emitted in all directions in space. There is the loss of much of the radiation and hence, loss of signal results. In order to maximize the amount of radiation used in the analysis, a mirror is located behind the burner to reflect the radiation back to the entrance slit of the monochromator. This mirror is usually concave and covers as wide solid angle from the flame as possible. To get the best results, the hottest and steadiest part of the flame is reflected onto the entrance slit. This helps to reduce flame flicker from the flame where light intensity reduces and noise is increased. The reflecting surface of the mirror is front-faced. If the reflecting surface is on the rear as in the normal household mirror, the radiation from the flame would have to go through the support material like glass or quartz twice before it is reflected to the entrance slit. Since the support material absorbs some radiation, there would be considerable loss of signal, particularly at the shorter wavelengths. Front surface mirrors are most efficient, but they are not physically protected. They are very easily scratched and subjected to chemical attack, e.g. from acid vapors in a hood. A care should be taken to protect them by keeping the instrument away from corrosive atmospheres. 3 slits. Entrance and exit slits are used before and after the dispersion elements. The entrance slit cuts out most of the radiation from the surroundings and allows only radiation from the flame and mirrored reflection of the flame to enter the optical system. The exit slit is placed after the monochromator and allows only a selected wavelength range to pass through to the detector. It is essential that, for many purposes, this wavelength range should be very narrow, which is necessary if emission lines from other components in the name have a wavelength similar to those of the emission lines of the elements being determined. The slit must prevent such interfering lines from reaching the detector. These slits in the monochromator system can be represented as shown in below figure. 4 monochromators. In simple flame photometers, the monochromator is the prism. But in modern and expensive models, the grating monochromators are used. Quartz is the most commonly used material for making prisms, even though its dispersive power is less than that of glass, because quartz is transparent over the entire region. The grating monochromator consists of a grating which is essentially a series of parallel straight lines cut into a plane surface. 5 filters. In case of some elements, the emission spectrum contains a few lines, where wide wavelength ranges will be allowed to enter the detector without causing any serious error. In such a situation, an optical filter may be used in place of the slit and monochromator system. The filter is made from a material which is transparent over a narrow spectral range. When a filter is kept between the flame and detector, the radiation of desired wavelength from the flame will enter the detector and can be measured. The remaining undesired wavelength will be absorbed by the filter. The flame photometers with filter monochromators are very convenient for simple repetitive analysis. However, such instruments can be used for a small number of elements. 6 detectors. The radiation coming from the optical system is allowed to fall on the detector, which measures the intensity of radiation falling on it. Any detector should be sensitive to radiation of all the wavelengths to be examined. In good flame photometers, the photomultiplier tube detectors are used, which produce an electrical signal from the radiation falling on them. 2.4 Effect of solvent in flame photometry. In addition to ionization effects and compound formation, it is necessary to consider the so-called matrix effects. These are the physical factors which will influence the amount of sample reaching the flame and are related to factors like density, viscosity, surface tension, and volatility of the solvent used to prepare the test solution. If we wish to compare a series of solutions, it is necessary that the same solvent should be used for each and the solutions should not differ much more in their bulk composition. This procedure is known as matrix matching. In some circumstances, interference may result from molecular absorptions. For example, In acetylene air flame, a high concentration of sodium chloride will absorb radiation at wavelengths near 213.9 nanometers, which is the wavelength of zinc resonance line, hence NaCl would represent an interference in determination of zinc. Such interferences can be avoided by choosing a different resonance wavelength or alternatively by using a different flame so that the operating temperature is increased, leading to dissociation of interfering molecules. For flame photometric measurements, solutions in organic solvents may be used directly, provided the viscosity of solution is not much different from the viscosity of aqueous solution. Again, it is important that the solvent should not lead to any disturbance of the flame. For example, carbon tetrachloride may extinguish an acetylene air flame. 2.5. Instruments. Instruments are generally designated as flame photometers. It is observed that the flame is much lower energy source than the electrical means of excitation. Thus, a flame produces a simpler emission spectrum with few lines. Further, relatively cool flames, e.g. air propane, are normally used in flame photometers in which the emitted radiation is isolated by an optical filter and then converted to an electrical signal by the photodetector. The following figure shows the layout of a simple flame photometer. The precision of the above technique can be improved by using a double beam, internal standard, flame photometer. The below figure shows a line flow diagram of double beam clinical flame photometer for study of Na and K elements. The electronic circuit is designed to give a direct reading of sodium and potassium concentrations. Nowadays, various sophisticated and automatic instruments are available in the market. 2.6. Experimental procedure of analysis. Flame photometric technique has number of applications in qualitative and quantitative analysis as follows. A. In qualitative analysis, flame photometry is only used to detect elements of IN2 groups of the periodic table. For example, sodium, potassium, lithium, magnesium, calcium, strontium, barium, etc. Some of these elements can be detected visually by the color of the flame only. For example, sodium produces yellow flame. But this method is not a reliable method. However, the best method to use a flame photometer with a monochromator or filter to separate radiation with the wavelengths characteristic of the different metals from other radiations present. The detection of the radiation of the characteristic wavelength indicates the presence of a metal in the sample. The flame photometric method for detection of elements is fast, simple and quite reliable if carried out carefully. However, this method faces with some difficulties which are outlined as follows. I. This method is less reliable than atomic absorption spectroscopy. 2. The method does not provide information about the structure of the compound present in the sample solution. 3. Non-radiating elements like carbon, hydrogen, and halides cannot be detected by flame photometry, but can be detected under special circumstances. For example, if chlorine is to be detected in a liquid sample, the best way is to precipitate it as silver chloride, which is then aspirated into the flame of a flame photometer to carry out determination of silver. From the result, the chloride content can be calculated. B. In quantitative analysis. This is the most useful application of flame photometry. This is used for the rapid quantitative determination of the elements in IN2 groups of the periodic table. If high optical resolution equipment is used, other metallic elements besides groups I and II can also be determined. The list of elements with their emission wavelengths and detection limits is given in the below table. These elements have been determined successfully by flame photometry. Experimental procedure for quantitative analysis. Whenever quantitative analysis is to be carried out, The first step is to introduce the sample solution into the flame, and then the intensity of radiation is measured at the proper wavelength. From the intensity of radiation, one can determine the concentration of metal present in the sample by employing any one of the following methods. A. Standard addition method. In this method, various solutions containing known and unknown amounts of standard substance are used. Here, the first job is to know the signal intensity for the unknown B by aspirating its solution into the flame of a flame photometer. Then, number of solutions containing mixture of the unknown B and various amounts of the standard A are prepared, and their signals are obtained by aspirating them into the flame. Then the plot of signal intensity, y-axis, against concentration of B plus concentration of standard A, x-axis, is drawn. From the plot, the concentration of the unknown can be determined from the intersection of the curve on concentration axis as shown in figure below. Advantages: I. The method is useful for determining very low concentrations of elements. 2. The method compensates for any unexpected interfering material present in the sample. 3. The method can be used to estimate those elements which are rarely analyzed. Precaution: in this method, a correction should be made for background emission from the flame. This can be done by injecting the solvent into the flame, and then its signal intensity called background emission is measured. During calculations, the intensity of background emission must be subtracted from the emission due to sample. B. Internal standard method. This method involves the following steps. I. Standard sample solutions containing known amounts of internal standard element, usually lithium, are prepared. Then, these samples are aspirated into the flame, and the signal intensity for each of these samples is recorded. 2. Now the samples having unknown concentrations are aspirated into the flame, and signal intensities are recorded. 3. The ratio of the two intensities is calculated and is then plotted against the concentration of the element to be determined. The concentration of the internal standard element is kept constant. A calibration curve is obtained, from which one can calculate the concentration of element present in the sample if its signal intensity is known by aspirating it into the flame. When this method is used with a simple flame photometer, the effects of momentary fluctuations in flame characteristics will not be eliminated, but this can be overcome by using a direct reading instrument which gives a direct and simultaneous reading of the two intensities. Every element cannot be chosen as the internal standard. However, it should fulfill the following characteristics. I. Its amount should be very small in the original sample. 2. It should give an emission line which reacts to interferences as the line of the element does. 2.7. Interference in flame photometry. Various factors may affect the flame emission of a given element, interfering with the determination of its concentration. These factors may be broadly classified as A. Spectral interferences and B. Chemical interferences. A. Spectral interferences. These arise mainly from overlap between the frequencies of a selected resonance line with the lines emitted by some other element. This arises because in practice a chosen line has a finite bandwidth. Since the line width of an absorption line is about 0.005 nanometers, only a few cases of spectral overlap between the emitted lines of a hollow cathode lamp and the absorption lines of metal atoms in flames have been reported. Below table gives some typical examples of observed spectral interferences. Some interferences may arise from the emission band spectra produced by molecules or molecular fragments present in the flame gases. Particularly, band spectra due to hydroxyl and cyanogen radicals arise in many flames. B. Chemical interferences. In flame spectroscopy, The production of ground-state gaseous atoms may be inhibited by two main forms of chemical interference, namely stable compound formation and ionization. A. Stable compound formation. It leads to incomplete dissociation of the substance to be analyzed when placed in the flame. Another possibility is formation within the flame of refractory compounds which fail to dissociate into the constituent atoms. Chemical interferences can be overcome in one of the following ways: I. By increasing the flame temperature. 2. By the use of releasing agents. 3. By the extraction of analyte or interfering element. B. Ionization. Ionization of the ground-state gaseous atoms within a flame, M- to M plus Ne, will reduce the intensity of the emission of the atomic spectral lines in flame emission spectroscopy. Therefore, it is necessary to minimize the possibility of ionization occurring by using a flame operating at the lowest possible temperature which is satisfactory for the element to be determined. The ionization of the element to be determined may also be reduced by adding an excess of an ionization suppressant, which is usually a solution containing a cation having a lower ionization potential than the analyte. Other effects. Besides compound formation and ionization, it is also necessary to study matrix effects. For details of this, please refer previous point, Effect of solvent in flame photometry. 2.8 Factors influencing the intensity of emitted radiation in a flame photometer. The intensity of emitted radiation in a flame photometer can be affected or influenced by various factors as discussed below. 1. Viscosity. The addition of a certain substance which increases the viscosity of solution, decreases the intensity of emitted light. This is observed due to reduced efficiency of atomization. 2. Presence of acids. The presence of acids decreases the intensity of emitted radiation. This decrease arises due to the disturbance of the initial dissociation of equilibrium. 3. Presence of other metals. The presence of other metals also causes the changes in the intensity of emitted radiation. To overcome this defect, special filters are used which will selectively absorb radiation from other metals. 2.9 Applications of flame photometry in real sample analysis. Flame photometry is used in variety of fields to analyze the samples which are summarized as below. A. In pharmaceutical industry. Flame photometry is widely used in pharmaceutical industry. I. To determine the concentration of sodium and potassium ions in infusion solutions such as NaCl solution. 2. To product control and indirect quality testing of various substances over sodium, potassium, or lithium. 3. To determine the concentrations of pharmaceutical industry. 4. In production of blood collection tubes. V. To check correct chemical composition of finished products. B. In food industry. I. To monitor the compliance with sodium and potassium limits in foods. 2. To check the quality of pre-milk, pre-food and milk powder. C. Beverage industry. To determine the content of sodium, potassium, and calcium in various liquids such as fruit juices, vegetable juices and soft drinks. D. In environmental analysis. I. To determine the quantity of alkali and alkaline earth elements in the sample. 2. To monitor soil qualities and water analysis. 3. To control the fertilizer residues in soils and fertilizer residues in water. 4. To measure impurities in water. V. To control and monitor discharged wastewater for potassium, sodium, and magnesium. E. Chemical industry. I. To final inspection for inbound inspection of chemical products. 2. To determine concentration of sodium and potassium in fertilizer products. 3. To check the ultrapurity of water. F. Cement industry. To take review of sodium, potassium, or calcium content in the construction and cement industries. G. Petrol industry. It is used to determine the quantity of lead in petrol. 2.10. Limitations of flame photometry. 1. Although flame photometry is a means of determining the total metal 1 content present in a sample, it does not provide information about the molecular form of the metal present in the original sample. 2. Flame photometry cannot be used for the direct detection and determination of noble metals, halides and inert gases. 3. Only liquid samples may be used, however, in some cases lengthy steps are required to prepare liquid samples. 4. Flame photometry cannot be used for the direct determination of all metal atoms. There is a limitation on the number of elements that can be analyzed by this method. 5. In the measurement of concentration of the metals by flame photometry, it is observed that relatively low energy is available from a flame and hence relatively low intensity of radiation is obtained from the metal atoms, particularly those that require large amounts of energy to become excited. 2.11. Conclusions. It can be concluded that flame photometry is a simple and rapid method for study of number of elements like sodium, potassium, calcium, lithium, magnesium, vanadium, trace elements, cadmium, zinc, copper, arsenic, nickel, etc. The procedure by which gaseous metal atoms are produced in the flame may be summarized as follows. Here, during aspiration of metals into the flame, the following events occur in rapid succession. I. Evaporation of solvent, leaving a solid residue. 2. Vaporization of solid with dissociation into its constituent atoms in the ground state. 3. Some atoms may be excited by thermal energy of the flame to higher levels and attain a condition in which they radiate energy. Thus, flame photometry is modern technique for study of number of elements in various forms.